Hello, and welcome to Undercooled, a materials education podcast. I'm back here again with my co-host, Steve Yalasov.
Hello, Tim. I'm Steve Yalasov at the University of Michigan, and today we're going to be talking about our bladesmithing class. It's not really a class, it's a club that Tim over here is in charge of. So I'm going to be asking Tim some questions about bladesmithing.
Absolutely.
So, Tim, why don't we start by you just telling me what is bladesmithing?
Sure. Bladesmithing is the process of forging blades. I guess I could just stop there and we could go home for the day. But what I'll say is that our club has a variety of students from lots of different backgrounds, not just material science and engineering, but from other engineering majors, from the art school, from neuroscience, from architecture. So it's really got a wide reach within the student community. And they work on a wide variety of projects matching their various different interests. So bladesmithing has always been a big draw and a main attraction for what the club does, but some students are working on anything from punches to bottle openers to Christmas presents for their families. It's a really great way for students to engage in life on campus beyond the classroom.
Wow, that's great. So how much relevance does this have to that TV show that I remember hearing about?
Are we allowed to name it on the air?
Sure.
Oh, okay. Well, yeah, Forged in Fire is a big hit among the students. In fact, we've had two members of the Michigan Blacksmithing Club on Forged in Fire as competitors. One of them has requested that his episode never be viewed again. But the other one, who is our current club president, actually placed very well and went through several rounds of competition. So we are very happy for him and proud to see Michigan represented on Forged in Fire.
Oh, that's great. Now, of course, TMS has had a competition that predates Forged in Fire quite a bit. Is that right?
Yes, that's right. And the TMS bladesmithing competition is how the club got started in the first place. We had a student 4 years ago who had a blacksmithing hobby shop at home before even coming to the university, and came to the university, declared MSc, and said, I want to see more students get into this in this major. How can we make it an academic activity? And so our department sponsored a bladesmithing team to go to TMS to participate in the TMS bladesmithing competition. And it was so successful that it turned into a bigger thing that turned into a sponsored student organization that is now the Michigan Blacksmithing Club.
Wow. And you were involved right from the beginning, is that right?
Yes, that's right.
That's cool. So there's two things though, right? There's the bladesmithing club and the bladesmithing team. Is that right?
There's the Blacksmithing Club, and a subset of the Blacksmithing Club is the bladesmithing team. So the team is the one who goes to competitions, both academic and outside in the non-academic community, and they're participating in these Forged in Fire-like events.
I see. So what are the kinds of blades that they're making?
For a lot of the competitions, many of them are historically oriented, and so it will be an opportunity to learn about different cultures at different times and places in history, and to see what sort of edged tools were important or popular at that time and place in history. So as one example, at the TMS competition last year, our students worked on a few different options that they were exploring, and ultimately settled on a really beautiful pattern welded knife inspired by the Bowie knife, which is an American classic, and that placed extremely well. They got an honorable mention place in the annual competition that year.
Oh, that's great. And so to actually do the bladesmithing, where does the material come from? I mean, do they just, I know on Forged in Fire, they like go to a junkyard and pick some stuff up, but you probably are a little more thoughtful than that.
Yeah, alloy selection is of course, a critical part of what the students do. And this is where they start to get into the material science aspect of it, is what microstructures all of these different steels have, how those will affect the properties of the blade, but also what will be doable with the tools and techniques that they have access to. So they're starting right away looking at it as a material selection problem and then going to industrial suppliers who sell billets of these different alloys and choosing from catalogs just like they would if they were producing an industrial product.
Now, I've seen our undergraduate lab and our facilities, and I don't think I ever saw anything that allows somebody to forge something. So how do our students actually do this forging?
Yeah, they have a space set up off campus that they are using, and they have a variety of forges. They have anvils that they've acquired from a variety of places, everything from farm auctions to eBay, and they have made a lot of their own tools at this point. That's one of the things that's so great about blacksmithing is it's the trade that makes the tools for the trade to make the tools for all of the trades. And so they're making their own tongs, they're making their own hammers even, and really taking it from the ground up. It's very cool to see how the club has grown over the last few years as they've developed these capabilities.
That's awesome. So the Blacksmithing Club, when did that actually start? What year did that start?
They became an official sponsored student organization at the University of Michigan just last year. Before that, it was much more of a, I don't want to say unofficial activity, but it was something that a group of students worked on every year, and they just sort of would recruit the next group of students to get interested in the next year's competition. This year is when membership has really taken off as the student community has mostly recovered from COVID and started to really engage with on-campus life fully again.
So how many students are in the club?
We have, I want to say, a little bit over 100 registered members. And then of that, there's a core of a couple of dozen who are every week going to these forging sessions and working either on competition pieces for the team or just on their own individual art projects that are of their personal interest.
Wow, so this seems like it's a lot of time for you.
Yes and no, it's not too bad because as with any student organization, the most important thing students learn here is not really the scientific content, it's the professional skills, right? It's the time management, it's the logistics, it's being organizers, maintaining their own schedules, recruiting new people, delegating responsibility among the officers. And that's where as with any teaching experience, of course, if you invest the time in the students up front to teach them how to fish for themselves in a manner of speaking, then they will go forth and fish. So at this point, I'm really proud of how self-sufficient they've become.
That's great. And you said obviously they're from more than just material science. Where are they from?
They are from pretty much every corner of campus at this point. And some of the advertising has come through official university channels, club recruiting events like Festifall. Some of it is also just word of mouth as well. It's the sort of thing that if students catch wind, I heard there's a blacksmithing club. I was always curious about blacksmithing. And one conversation leads to another, and suddenly they're getting, invites to the club Discord and showing up at forge sessions. And it's grown very organically, which is wonderful.
That's great. So a lot of clubs at the University of Michigan have people who are from the community and not even students at the university. Is that the same with the Blacksmithing Club?
In this case, all of the club members are students at the university, but something that the students have started doing this year is to engage a lot more with the community outside the university, which is great. In Southeast Michigan, there are quite a few blacksmithing events and organizations that have members just, in the general public. And that's something that I've been really happy to see the students engaging with this year, because there is a world outside of academia, and there are a lot of valuable connections that they can make in that sphere as well.
Fantastic. And so I imagine that the students learn a lot about material science while they're doing things in the Blacksmithing Club. Is that true?
Yes and no, because as we know, students will choose to learn the things that they choose to learn, regardless of what we have planned for them. So I will say certainly for the bladesmithing team that is doing these competitions, very often scientific analysis is part of the competition itself. And that's a place where especially our MSc majors have excelled and been extremely competitive, placed very highly, is doing very thorough, very rigorous scientific analysis of the blades that they are forging from a tetrahedron point of view, really getting into structure property relationships. And then on the other side of it, something that I think is great about the club being inclusive and having such a diverse student membership is some students just want a social activity where they bang on some metal once a week and have friends and just get some creative outlet from that process of making something themselves. And it really does span that whole continuum between those two extremes.
That's awesome. So do you ever convince anybody to switch their major and become a material science student?
We've got one or two. It's, I wouldn't say it's a primary recruiting mechanism for any program chairs out there who are trying to boost their numbers. But where I would say it's very successful is that we get some students who are in that MSc curious pool, especially freshmen, and they might come to an open house or come to a majors fair. And they'll say, so what do you do in MSc? And I'll say, did you know we have a blacksmithing club and you can join it and be integrated into academic societies and meet people in the community and forge, all of these different project options. And they say, wow, that sounds really great. Count me in. So where I've found it to be best for recruiting is for locking in those students who are considering MSc but haven't fully committed yet.
So maybe we should make a little promotional video for the Blacksmithing Club to help with those efforts.
I think that's a great idea.
Okay, we'll do that. And back to the societies. Are we going to go to, is it TMS that you go to in the spring?
Yes. So every year we're participating at the TMS Bladesmithing competition. That is how the club started, and it's still our core academic.
So what's up for this? Are you allowed to say what you're working on, or is that a competitive problem?
Well, I don't want to give away too much just in case the opposition is out there. But I will say that this year's blade has a plan to integrate a functional materials aspect to the design. It is not going to be a purely structural project.
Wow, that sounds exciting. Do the team ever take advantage of our new casting facility in terms of trying to create a specific alloy that they can actually make the alloy and then go work it?
This has been a topic that gets discussed every year, and where we're often limited is in making sure that we are sticking to the rules of the competitions because, as I was saying earlier, many of them being historically oriented also expect a certain use of historically accurate materials in cases where that's relevant to the blade being chosen. But others that do have more freedom of design, we've talked a lot about actually customizing our own alloys where that would be relevant to the project that's being submitted. So it hasn't happened yet, but I do think it's just a matter of time.
That's really cool. And I guess finally, is this something that you would recommend that other universities take up? I mean, is this widespread? Does every university that has a materials program have a bladesmithing team or a blacksmithing club?
There are a few, but it's certainly not universal. And I would say that it's a great thing for the students. And at the end of the day, that really is what it's all about. It's a way for them to build out their social networks, to engage in these professional societies, to build their creativity outside of solving differential equations every week. And I think it gives them a really well-rounded experience that still lets them engage with that material science and engineering way of thinking that we're hoping to help them develop. So I think it's a great opportunity for any materials department to host something like this.
Well, that is absolutely great. Thank you so much, Tim, for telling us about the bladesmithing team and the blacksmithing club. And I look forward to seeing this new competition at TMS.
Yeah, I bet we can shoot an episode there and maybe talk about how things are going as the competition is revealed.
That would be awesome. At any rate, we're going to do our typical session of me admitting to you what my problems were in teaching this week, and hopefully you'll do the same.
Absolutely.
So I guess I can go first. So I'm teaching our introductory materials course. And we're near the end of the term. There's only, 2 more classes left for me. But this is actually my favorite part of the course because we're finally talking about electronic materials that are near and dear to my heart. And everything is great until I start to open my mouth and I realize, I have students in here. Our only prereq is a freshman chemistry course. Physics is not a prereq for this course. And all of a sudden, I'm faced with the same dilemma I have every year. How do I explain what a band gap is? And I'm so torn. And because the only way I know to explain a band gap is to explain the quantum mechanics, the statistical mechanics, and the solid state physics that go into, a Fermi-Dirac distribution. The fact that electrons have to be in states, only spin up or spin down, the occupancy, and then the concept of a periodic array of potentials and how block states allow us to actually solve the Schrodinger equation. And with those few sentences, I think you can quickly realize that's several courses of junior level physics that have to be understood because they do it. And then added to that complication is the fact that I hate the way the physicists do it. Because the classic way to show what a band gap is to do the Kronig penny model, where you solve the Schrodinger equation for a periodic array of potentials. And with periodic boundary conditions, you quickly find the solution is a transcendental equation that you can only solve by plotting it. And when you plot it, you can show that solutions only exist down here and up here. And there's a region in energy where no solutions exist. Aha, done. Too bad there's absolutely nothing physical about the physics description. It's a mathematical description.
Yep. I remember dealing with that in my graduate solid state physics course and finding it completely impenetrable from any point of view of thinking about, but what are the electrons doing?
I know. And so I think the answer is to think about something that makes most physicists shudder. The answer is in chemistry. The chemists have developed this concept of molecular orbitals, where if you take two atoms and you bring them together, their energy levels are the same. But when they bond, you form a lower energy level, and they call that the bonding orbital. And with every bonding orbital, remember those little dotted lines? They have an anti-bonding orbital. And no one knew what that meant, including me when I took chemistry. Like, what are you talking about? That's from Star Trek or something, antimatter, reactor and all that junk. But what it means is that's how much energy you need to break that bond and pull those atoms apart again. That's the anti-bonding orbital. So once you have a bonding orbital, you absolutely have a fictitious but real anti-bonding orbital, which represents that energy needed to break the bond. And then if you take that simple concept and then you use the Slater concept of taking atoms far apart and bringing them closer and closer together, forming bands from each discrete state of the atomic state. When you bring lots of atoms together closer, you get a band of states. And then I like to tell my students about how everybody abuses the word quantum leap. Right? Everyone makes it sound like this giant thing.
It's the tiniest possible thing.
That's right. It's like 10 to the minus 7 EV. It's barely measurable. And it's the change in energy from one state to the next state within a band. But once you fill up those bands, so anyway, if you start with a molecular orbital model with that little bonding state, when you bring in lots and lots of atoms together, that single bonding level builds to a band of states where each state is very finely divided, 10 to the minus 7 EV, and that's your valence level. And if it's a metal, you're partially filled. So the next available state is to hop up. And I like to tell them about how physicists lie to them about the Fermi bit level being the level of the highest energy electron at absolute zero. But, and it's kind of true, but a better definition, I don't really know why they don't say this, probably because it's not right. But I like to think about it as the Fermi level is halfway between the lowest occupied state and the next available state. So if it's 10 to the minus 7 EV, that's even a smaller number So you may as well just say it's the highest energy electron, the highest energy state at absolute zero. It's pretty good. But when you get to a semiconductor where you have covalent bonding and all the atoms are shared, you've occupied every single state in the bonding band, and there are no more states, and every electron is accounted for. And the next available state is in the next band of unoccupied states at absolute zero. And so the distance from the top of the valence band to the bottom of what we call the conduction band, because of course, nothing can conduct unless they're not next to other particles in the same state. You have to hop them up to the next state. And we have all these really cool analogies, parking lot analogies, like you're on the freeway in LA, and either you have your violent option of what to do with your machine gun mounted on your car and you blow a hole through, or your much more pacifist, progressive model of being like George Jetson and just levitating up and driving along the top of all the other cars because you just don't want to deal with them. Well, that latter one is how conduction in metals works.
Right.
And in a semiconductor or an insulator where everything's filled up, the only way to get to that next state is to break a bond. And when you break a bond, that amount of energy is in the molecular orbital model going from the bonding level to the anti-bonding model. Now, I know that's not exactly correct because there are some minor differences. And in higher level courses, we learn about the, chemical potential and all these things. But it doesn't matter. What matters is I just want to explain to them that a band gap represents the energy it takes to break a bond to allow an electron to get up to a other state. And by now, if you're listening to this and you don't know anything about solid state physics or statistical mechanics or quantum mechanics, you're probably wondering, why are you going blah, 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 blah? Because I don't understand a word you're saying. And that's my problem. And that's the problem I had in class today. And I don't know how to solve it. All we do is we then give them much easier problems, try to explain why the Fermi level is in the middle of the gap for an intrinsic semiconductor, why when we add impurities, it's easier to break those bonds because they're very loosely bound to this extra atom. And so the Fermi level then is halfway between the virtual state and the bottom of the conduction band for a donor. And for an acceptor, it's halfway between the top of the valence band and the donor level. But it's hard. It's really hard to explain all these mid-gap states and all of that. And it's just all so important. It's so important they learn how to use this because these mid-gap states are what's revolutionizing solar energy with, mid-gap, solar collectors or, mid-gap defect states and things like diamond that might be the solution for quantum computing and all of these things. It's such a beautiful field and it's so hard to teach at this introductory level. So that's been my problem. How about you, Tim?
So, Steve, what I was thinking about as you were describing the difficulty of teaching this topic is how this is such a good illustration of these two dilemmas that we always face as teachers. The first one being, how much do I simplify the content? Because we're always choosing some assumptions to make, some complications to leave out to make sure that the topic is appropriate for whatever level you're working at. And the other dilemma that we always face is, how much do I focus on the applications and why it matters versus getting down to the underlying fundamental science of why does this work and why is it interesting? And it's lovely to dream about doing all of those, but that's often not possible from a time point of view. And just wrestling with this decision is one of the eternal struggles that we face.
Yes, it is. And our poor students are often left just wondering, well, what am I supposed to do? Mm-hmm. And I feel bad for them. And I wish there was an easier way. Science is so hierarchical. You need to know so much before you go to the next step. Mm-hmm. And it's why it's why thermo is difficult. It's why a lot of these concepts are difficult because it really just takes time to really reflect on what all this means. And even if the material's really not that hard, to describe, there's a lot of steps.
Mm-hmm.
And, it reminds me of how many people abuse the term rigorous. People use rigorous when they really mean really difficult. And that's not true. If you're really rigorous, nothing is difficult. Rigorous means you actually include every single little step and don't leave anything out. And when you do that, it's pretty easy. It's simple. But people abuse that all the time.
Indeed.
So how about you? What problems have you had teaching this week?
Oh boy, where do I even start? So this is the last week of labs for me. And so all the students are in crunch mode of making sure they get the last data that they need for their final projects and looking at what they've collected so far, doing that sort of real-time analysis, figuring out what are the gaps in the work that they've accomplished so far, which is great. I'm very happy to see them practicing that awareness of their progress in real time. But I had a team who was looking at the Young's modulus for this alloy that they're trying to improve and realizing that the tensile data that they have simply don't let them make a good modulus measurement, which is not entirely surprising, but was something that they really were grappling with all of a sudden, that our entire plan was to talk about how we change the modulus, and we just realized that our measurement for the modulus is bad, and it's the last week of lab. What do I do? Just, give up and go cry in the corner? And this is a thing that even as researchers, of course, we struggle with this, where we think we've finished a project and then we realize, especially if talking to a reviewer, oh no, I left out something important. And it's a perennial problem for me dealing with the artificiality of the class experience, that then it ends and students, maybe they've finished, maybe they haven't, but I can't say go back to the lab and do it again and do it right this time, because the course is over and there's no way for them to do that. So this is one of my problems that I think about every year and never solve, is that what's the best way to handle a situation where students realize they should have done something differently and there's just no time to go back and do it again the way you would do in a research lab.
Have you considered having them write about it?
Oh, absolutely. And that's what many of the students do, is as they're giving their presentations, they do a great job of describing, here was my original plan, and then I realized this problem with my original plan. Here's what I pivoted to instead. And they handle it very professionally, and I'm usually very impressed with how they do that. But it does just lack that satisfaction of actually accomplishing the thing that you set out to do in the first place. And it always feels a little like a missed opportunity there.
Well, that's kind of how most research is.
It sure
right?
is.
I mean, a good outcome for a research project is when you create many more problems than you had when you first started, because then you're on to something new and it never really finishes, right? Research is always very, very open-ended. Once in a while, you can take some information from research and find an application for it and make a product and all that, but you probably still haven't finished all the science, because science goes pretty deep. So that's a common experience in any research project. Just go back to think about your own PhD. It probably ended with, geez, if you only had another year or two to keep going. And the problem is you'd keep saying that because it would never end, because we keep discovering new things and new relationships and new physics. And that's kind of what makes it so exciting to do.
Yeah, and that's the goal for the students as well, that they gain enough knowledge and enough perspective to look back and say, if I had only known 6 months or a year ago what I know now, what I would have done differently. And that's where a lot of these conversations end up, is just trying to help the students appreciate that they have gained that perspective. And maybe that's not what they expected to get out of the course, but it's absolutely a valuable outcome.
And it's kind of the basic fundamental reality of engineering. It's never the right solution. It's always the best solution, because we can't always find the right solution. everything's over constrained. There are too many variables. And so what do? You do whatever you can do to make your product as good as you possibly can and work as safely as you can. And everything's a compromise. And we just have to learn how to live with that, because that's life.
Absolutely.
And so with that, as we've had our own difficulties with this podcast, maybe you can hit that button, and we'll say goodbye until next time.
I think so.
Great.
Thanks for
See
coming,
you later.
everyone.